We are very happy to have Kris Brown with us, who will be telling us about combinatorial representations for scientific knowledge.
Cool, thanks. Yeah, so I'm currently a postdoc at UF, working with James Fairbanks. But prior to that, I was actually a computational chemist, and I experienced a lot of problems, sort of systemic problems there that I think in my current role and working with the Topos Institute that we're working towards addressing. So hopefully, if you're also a computational scientist, that your interest is piqued and that maybe there are some tools that can help you as well. So I want to start by contrasting with what I see as a status quo for representing scientific knowledge. This is a small Python script where the kind that I would write all the time, where you have some real-world data, you initialize some conditions and make a little for loop, and you simulate a chemical reaction. You compare the results, you generate a plot, and that goes into your paper. And this is kind of self-contained. Normally these scripts are calling each other in some big labyrinth. But so this plot and the paper it's in is an important form of scientific knowledge. It's very valuable, but it's not of interest in this talk because it's informal. And because it's informal, it means in order to understand it, a human has to mediate it, and you can't use any kind of tools with it short of NLP. And so the problem I'm concerned about is a scientist sees this figure, wants to know what's behind it? What does this mean? What's the thing behind it? And if the scientist were to demand a formal object, a rigorously defined thing that explains that plot, there's really nothing that they can be pointed to other than this script. There's nothing else to point to, and that's just the reality that many scientists find themselves in. And so you can ask, what's the downside of that? And an abstract critique would be that as a representation, as a model, this conflates data, syntax, and semantics. But as a pragmatic, practical objection, we might say there's just lots of really cool things that we would like to do with models that we can't do if this is the form of our model. We might want to have some language to declare our assumptions about the world, and when those change, we want our whole model to change, and that just can't happen with code like this. This script itself was the product of tweaking these various parameters and rates in order to get something that matched experiment, but that whole trajectory was lost. We don't have any record of that, and moreover, it's somewhat of a tedious process that could stand to benefit from automation, and that sort of exploration process is not possible with, or it's not facilitated at least by this kind of model. You might wonder why do we even need to write this code at all? In my doc string, I wrote the chemical formula and I wrote mass action kinetics. Why isn't that enough to do? Why did I have to define my model mathematically and then completely separately try to implement it and hope that I did that correctly? And another thing that scientists want to do is check whether two models are the same in some sense, or one's a submodel of the other. That is not something you can do just comparing this script versus another script. And lastly, if I want to change the semantics, an example of that being, well, I want to also simulate this reaction, but I want to do a stochastic-based model rather than this sort of ordinary differential equation model. Now I have to start from scratch again. So these are all examples of things that can't be done, but what I'm going to try to convince you this talk is that there's another way of structuring the scientific knowledge that's lying underneath the script in a way that makes these kinds of tasks facilitated. So I'm going to give the talk in two halves. First is going to be more focused on breadth. And the second one will pick a particular example and go more in depth. So I'm going to start by saying, where do we want to apply these combinatorial data structures? I will then actually tell us what they are in more detail, some algorithms that help us manipulate them, and really focusing on why do they provide a more hygienic form of scientific knowledge representation. And during that part of the talk, I'm going to say a lot of, we can do this and we can do that, and you'll have to take me on faith, because the second half of the talk, I will go into more detail in a very specific example, and you'll get to see more of how these tools work. So to begin with, just a prerequisite for anything is just representing a model. How do you encode that data? And I would say the status quo here is to have an informal diagram, and then that conveys some intuition, and then you'll accompany it with some mathematical formula or perhaps some code to make very precise what you mean. So let me do that for this particular model. So the informal diagram says, it's called an SIR model. It will show up many times in this talk. The informal model says people start out susceptible. At some probability, they become infected, and they eventually recover. And the formal expressions that formalize this say there are two types of transitions. There is one transition where a susceptible and infected person meet, and two infected people come out of that. And there's another transition that's possible where an infected person spontaneously recovers. And what our perspective on this is that we can actually do a little better than this, because similar to this informal diagram that was very intuitive and visual, there is another type of diagram that's a visual syntax that can represent these same equations. This you can see by counting the number of arrows in or out of these orange squares that we actually have all the information to losslessly regenerate these equations from this. And so this is called a petronet. And that might seem, it seems like a small advantage that it's visual and maybe a superficial difference. But I'm going to try to argue that this is actually a really valuable form of encoding these reactions. And we'll especially see that now when I talk about if our model has certain constraints. So let's say we want to restrict the number of reactions that we're actually considering. So for example, with a chemical reaction network for gas phase, we often only care about reactions that have two things hitting each other at once, or one thing. If you have three things hitting each other at once on the left-hand side of a reaction, that's not valuable. So the question is, how do we encode that kind of constraint with these symbols, with these symbolic expressions? You can sort of write whatever symbolic expression you want there, and it doesn't inherently, by construction, enforce some kind of constraint like this. And another example would be to label your chemical species as reactive or inert, and then add this constraint that you can't have a reaction where two inert species actually react and create something new. So we want to exclude these types of reactions from our class of models. But if we're working with this symbolic syntax, we actually can't do it. What I'm going to tell you, and it's kind of a teaser because I'm going to actually explain what it is in the second half of the talk, but there is a diagrammatic syntax that is extraordinarily similar to these petronets that actually lets you enforce these kinds of constraints by construction. Meaning, if you can draw the figure of the particular shape, you actually automatically will enforce these types of constraints, and you'll be able to represent anything you want. So that's a really powerful idea, and we'll show an example of that in the second half. To talk about applying these data structures to comparison, here is a different kind of combinatorial visual syntax for partial differential equations. This is a work of Evan and co-authors. And there's something really interesting you can do here if you want to compare. These are two different representations of heat equations. But if we represent the physics with this diagrammatic syntax, there's a decidable algorithm that will let us check whether the solutions of this heat equation is the same as the solutions of that one. And if you had compiled these down to differential equations, the sort of raw symbolic differential equations, suddenly there's no algorithm which will tell you whether or not they have the same solutions. In some sense, the language of the diagrams is actually constrained in a way that we can infer these sorts of things about it, which is a very practical thing to want to know. Another application area that we want to try to solve problems in is this problem of model exploration. And I'm going to formally define that problem when we get to the second half of the talk. But to begin with, I want us to consider what is the right notion of a combination of models. So here I have an SIR model, like I showed earlier. And here I have a two-city model, where you have people in city X, people in city Y, and you can move back and forth. So the question is, how do you faithfully combine the ideas of those two models? And it turns out that by representing them as petronets, we actually have a natural notion of a product which will tell us this is what it is. Essentially, you have susceptible people in city X, infected people in city X, recovered people in city X, and ditto for Y, and people can move back and forth. So this was a natural thing that came out of representing these petronets as these equations as petronets. And if you had just viewed these as the symbolic expressions of certain possible reactions, taking the product would no longer be meaningful. So having this structure ends up being useful for this task as well. And the last application I want to highlight is what I had mentioned of we want to define a reaction symbolically and graphically, and we shouldn't have to write code which performs the right kind of simulation. In this case, generating something which takes in initial parameters and conditions and simulates out the differential equations. And so we're really imagining a world where scientists can really stay focus on their domain of expertise and not have to also be computer scientists. And so, yeah, that was a whirlwind of applications very quickly, but I think it's good to know what the motivation is for, why should you care about what these combinatorial structures are? You should know that they are going to be used for solving really important problems. And so now I want to say more about what they actually are, but it's also a good caveat that it's not really necessary in order to apply this kind of technology, you don't actually have to understand what goes on underneath it, but I think it's good to show that anyways. But just to say that this might be quite abstract, but it's not essential in order to use the kinds of tools that I'm talking about. So I want to introduce the idea of a combinatorial data structure, and in an informal sense, I would say that these are data that have elements that are linked together in some way, where their connectivity matters, not their identity. And so we can start with a set, which has it's just a bag of unconnected elements. The structure of a set is really trivial. It's just a dot, you would say. A function is really our basic building block for connecting elements living in different sets, as you can see as an example there. And a graph, if you're not familiar, is this notion of you have edges, you have vertices, and every edge has a source vertex, and every edge has a target vertex. And with that reframing of what a directed graph is, then it's no more than just a set, two functions between an edge set and a vertex set. And so you can see each of these is going up a level of abstraction. We have no functions, one function, possibly many functions. The next level of abstraction is quite different in the sense that it requires us to think of what I've been putting in this box for structure as itself a parameter. And we want to be able to throw an arbitrary graph in there. And when we do that, we get something called a cset. So C is going to be the name of this structure, this parameter that I'm going to stick in a graph here. It turns out it's actually a category, which is why it's called C. But so for a particular choice of that, you get a whole data type. And so I've drawn one here, and I've sort of suggestively drawn the vertices, where it turns out that this network of 4 sets and 4 functions actually corresponds to precisely the petronets that we talked about earlier. And the way that works is that we have a set of states, we have a set of transitions, and we also have a set of inputs, which say for each one of those, they tell you a particular state is the input to a certain transition. We also have a set of outputs, which say a certain state is the output of a certain transition. And so when we visualize that, you see what we did before. There's also this more database representation of this, where you represent each object as a table, and the outgoing arrows become columns. So if you're familiar with databases, then think of C as the schema of a database. And so because we have the expressive capability of databases, we really can represent a really wide variety of models. But nevertheless, these are really easy to compute things with. So it's a really, I would say, a sweet spot in terms of abstractions. It turns out that C-sets are really just the starting point for a lot of the combinatorial data structures that we'll end up using. but I'll introduce those as they come up, as necessary, and really a cset as a type of model is a particular way of representing models is really the key takeaway. I think I was going to show some algorithms, but in the interest of time, I think it's better to see why are those combinatorial data structures actually providing us, why are those actually helping us achieve those applications? So I'd say the first virtue is transparency or predictability. This means that because our data structure has this notion of, it has an explicit structure, we can look at that and see what assumptions were made very easily. So for example, if someone gave me a scientific model and said, oh, and it's a petronet, I suddenly know what its limitations are, that it really contains nothing more than this connectivity between states and transitions. Furthermore, we can look at an individual instance of that, and I can say a very simple computer algorithm could look at this and say, well, I can tell that the recovered population is just going to strictly increase over time, for all possible assignments of parameters. And that's sort of an inference it's a very simple inference. It's one that you can't make on the example of code that I showed in the beginning. And really what this is related to is the fact that we're representing our model itself as data rather than code. And data can be processed by algorithms and analyzed in an efficient way. These examples of things that we could see transparently, I think, are very simple or trivial. And later I'm going to show like a very non-trivial type of transparency we can get. So generality of scope is another virtue, I think, of these data structures, mainly because lots of different applications share the same syntax. So I'm going to introduce a new cset here. This is a cset of wiring diagrams. And they're really good at representing general processes. So this is a sort of intuitive one for the process of making a pie. But it turns out that exact same syntax can be used for reasoning about mathematical equalities. They are sort of proofs of a certain sort. And furthermore, you can represent even all of linear algebra with this syntax of string diagrams. And although there's a learning curve, it ends up being actually a really natural way of expressing those ideas. And so when you write code for wiring diagrams in general, suddenly you see, wow, lots of different types of applications you're implicitly writing code for. And moreover, if you write code for csets in general, you can see that this is just one cset, and petronets were another, and graphs were another. So the fact that syntax and semantics have been explicitly distinguished means that it's much easier to generalize our code. Transferability is another virtue, I would say, that comes from this. So this is that thing I mentioned where we have sort of our model of the world, and our model of the world has been updated. Let's say that we have a model of the world where there's reactions and reaction networks, but we suddenly realize that our results were really dependent on what solver we had used to compute certain properties of the reaction. So it turns out we actually need to migrate our whole infrastructure from the old model of the world to the new model of the world. This is definitely something that we can do with sort of SQL and querying a database. But to be able to do this in a way that's both automatic and has a sort of guarantee of the correctness of it is a really powerful idea and will save lots of tedious and error-prone work. The last virtue that I want to highlight is hierarchical design. So the example that I want to use to demonstrate this is the notion of querying a database, where, if you're not familiar with that, querying a database is you have to write in a very special, weird language if you want to extract data from big data. If you want to look for a pattern, imagine some gigantic petronet. So it turns out that this is the language, this is SQL, but it also turns out there's a special diagrammatic syntax of undirected wiring diagrams which corresponds to these queries. And so again, you might wonder, well, it's nice that it's visual, but what's the difference? And one difference is that there's a notion of substitution that's entirely natural for taking a query and sticking it inside another query. In contrast, the syntax of SQL queries doesn't have this compositionality. You would take a long time to write an algorithm which does all the right renaming to do this same kind of thing. So the sort of composability would let you build a big query hierarchically from smaller queries. And yeah, that was broad, that was very fast, but the recap is that you can do a lot of things that are just not possible to do when your model is represented with one of these types of structures that are just not available if you think of a scientific model as a piece of code or some even mathematical equations. So now I want to really switch focus to some specific projects. And there's a lot of things that we're doing in AlgebraicJulia, in particular our research group. And now I've taken the 4 sections of the first half of the talk and laid them as sort of axes along the side. And I imagine each of these sort of projects as taking some part of the applications, some subset of the structures are relevant, some of these algorithms are relevant, and some of the virtues are really on display. And so for each one of these, I could draw a connection to all of these. I've been strongly advised to not draw them all at once, so instead we'll really just focus on epidemiology and draw them one at a time. So I want to first talk about this process of model specification. So how do we actually encode constraints in a way that the data structure itself is encoding a constraint? So just to review, our particular model right now is going to be these petronets, which are csets that have this shape for the structure of them. And again, this is what an instance looks like. And the semantics is going to be these reactions. And if we wanted to assume even more, we might assume mass action kinetics, in which case we're implicitly saying these correspond to these ordinary differential equations. So if I were to just stop here and say this is our model of epidemiology or our model of chemistry, it wouldn't be encoding that much scientific knowledge at all. It's not saying much just from this data structure. And so in order to move forward, I need to introduce a new combinatorial data structure. So this one is called a cset transformation or a homomorphism or a morphism, lots of names. But the key structure of one of those homomorphisms is that you have a domain cset and you have a codomain cset. And for each of the parts of the petronet, which is the states, transitions, inputs, and outputs, you have to give a function that maps the states of one to the states of the other, and so on. What that means practically, I have an example here where sort of the coloring is saying that these 3 states are being sent to that state, and these 3 states are being sent to that state, and the sort of coordinate here is telling which box the boxes go in. So the key thing to understand about these cset transformations is that not any assignment of these functions is going to be a valid one. It turns out that there's a sort of implicit logical constraint of these csets, which is that you have to, in some sense, have a continuous deformation of your domain cset into your codomain cset. You essentially need to preserve the structure in some way that could be made precise. And if you do that, you have a valid cset transformation. So you can't just randomly assign things here to things over there. And because of that, that means that our codomain, in some sense, is a constraint on our domain. To be able to map into this in a continuous way, it somehow restricts the possibilities of things that we can have up here. And so let me show an example of that. So if you have a model of hosts and vectors that are infecting each other in some very particular configuration, this host vector model is encoding some domain knowledge. What it's saying is that there are 2 types of species. There's hosts and there's vectors. And the only types of transitions that are possible are ones that have a host come in and a host come out, a vector-vector transition, and then a human and a vector interacting. And so you have a particular model that fits that structure. But if you hand this off to your collaborator and they add an extra transition, which converts a host into a vector, suddenly we can check very efficiently and very quickly that there exists no homomorphism from that petronet to this petronet. So this shift of perspective that the model isn't a petronet, the model is a homomorphism into this particular Petri net that encodes your domain knowledge, that's a really important perspective change, because that allows us to rule out a massive number of Petri nets that are actually not the types of things we are interested in. And so again, this is our domain knowledge down here. And I think furthermore that we get this benefit that our original Petri net actually gets labeled in some sense by the data of that homomorphism, which makes the Petri net itself a lot more interpretable. And secondly, that this process of looking for a homomorphism is something that can be automated, which means it's a form of type inference. If you had a partially labeled piece of input, we can tell whether or not it's ambiguous in some way, or if it's not satisfiable, if there's really exactly one way to make it fit your model. So in summary, we're able to represent these logical constraints with a purely structural piece of data, which is called a homomorphism. It's also called a slice. So, and I really think this example could demonstrate all the virtues, but I think it's most relevant for transparency, because you can look at that type, you can look at that codomain and infer a lot about what the model is doing, even without getting into the details. So now I want to return to the model exploration problem, but continuing with these disease models. So the problem statement is, given this class of models, so we're going to say the scientist has already restricted their attention to Petri nets as their models, and given this data, which is some real-world SIR data that you've collected, what is the best model that represents the data? So this means that we had a Petri net, the SIR Petri net, and now we want to update it in some way. We're using that Petri net in order to interpret this real-world data, because data never comes uninterpreted. Data is always ingested with respect to the current model. But now we want to say, well, how do I update my model in order to better account for this data? And the problem is really, there's an infinite number of models, and if we think of it as a set of models, a set has no order. There's, if the models are going to be explored, the scientist is going to impose a structure on it one way or another, and our goal is to try to make that process that the scientist is going to do anyways, make that explicit. And so we're going to try to find a structure that actually encapsulates this procedure for looking through this space of possible Petri nets. And that the name of that is called a diagram. So I have a new data structure to introduce to you. The structure of a diagram in Petri is you have a shape of some sort, which is like a graph, and you somehow map that into this whole space of possible Petri nets. And if it helps you now think again of what a cset is just a diagram in set. You have a shape, and for each vertex, you're going to assign a set or a function. So in this case, for every single vertex in this shape, we will assign a Petri net. For every edge, we're going to assign a Petri net morphism, exactly the same kind of morphism I talked about in the previous story. So I'm going to visualize the example with its own column, because it's quite big. The diagram has its own structure, which is what the shape is. And so if I pick this structure, which is just this graph with 4 vertices and 5 edges, the actual data of the diagram ends up having a Petri net at each vertex and implicitly a morphism for each edge. So that seems like a natural generalization of C-sets to just say, well, what about diagrams and other things? The real subtlety here is, what is the right notion of a morphism between diagrams? What's the right notion of a structure-preserving map between this massive amount of data here? And that's a pretty technical thing, and I hope that you can I'm not going to give an example. It's way too big to actually visualize. But trust us that we have like a good notion of what that is. And now we can ask, well, what good does this do to us? Like I said, that a model space is a diagram in Petri. How do we benefit from making that leap, let's say, and formalizing it that way? And I think the answer is that category theory gives us a lot of ideas for things to do with diagrams. And it turns out very natural things to do with diagrams are things that we already wanted to do with model spaces. We didn't have a good vocabulary for it, and we didn't know how to make it formal. but now we actually have a rigorous description of things that we wanted to do with model spaces, and we have concrete algorithms to actually implement them. So what's an example of one of those things? I think a product model space is like a very common thing that a scientist wants to do. So the setup is that there are sort of multiple dimensions that a scientist wants to explore when picking models. So if we think of a city dimension where we have a 1-city model, a 2-city model, a 3-city model, and so on, and now we have another dimension which actually has the disease dynamics. So we have the SIR model, maybe we have the SIR model with an extra transition, which allows people to go from recovered back to susceptible, which is more realistic. And this could go on. And so the idea is, I mean, in reality, yeah.
Sorry, guys, question. From the 1-city model to the 2-city model, are there 2 morphisms that you want to have, or just?
Yeah. So you definitely could. Yeah. So this is I'm picking that this is by my labels. I guess I'm saying this is X, that is X. So yeah, it's important to know that like the data of this diagram. So this is a diagram that I've laid vertically, and this is another diagram that I've laid horizontally. It's important that the data of this diagram not only includes the petronets, but also the maps in between them. Given that, though, a sort of natural thing that, like intuitively, a scientist would then write a double for loop, let's say, and loop through all these possibilities, and at each point in the for loop, compute a combination of those 2 models. And so how we're encoding that is with this notion of, well, it's actually a pullback, but we have this notion of a product. It's a type of product where if we take the product of these two diagrams, we actually get a resulting diagram, which is this grid-like diagram. And if we look at what lies underneath one of these vertices in that shape, we'll see that we get precisely what I showed you in the beginning of the talk, which was what's the right way of combining a 2-city model with an SIR model. So we've now, one advantage of sort of expressing this double for loop as this like formal structured object is it makes it much easier to plug into other types of transformations that we want to do. Essentially, these abstractions are much more composable than sort of arbitrary code blocks. But there's even another advantage, which is this notion of provenance. So once you produced that model inside of your for loop, you've suddenly lost the connections it had to the inputs that went into it. But with this notion of a pullback, we actually retain these connections. Let me show an example of one potential place that's useful. If we knew ahead of time that 1/3 of people lived in city X and 9 out of 10 people were susceptible to a disease, I think it would be a reasonable guess, at least as a first approximation, that 3 out of 10 people are susceptible in city X. And so these types of projection maps are precisely the sort of data that we keep track of. And this is not arbitrary, but this notion of product and projections, those come very naturally from the math. I want to also show that there's a dual notion to this pullback or product that's called a pushout, and that lets us create branching structures. And we can branch at the shape level. We can also branch at the underlying petronet level. So this is an example where I have some sequence of disease dynamics I care about. Now I have this idea of a death transition, which takes one from infected to a dead state. And what I want to do is I want to basically glue this on to everything in that sequence. And so this idea of a pushout also does the right thing and attaches it in the right place for the entire sequence of models. So this is all to say that these very intuitive ideas of how do I not only combine models, but entire spaces of models has been made rigorous with really, really basic constructions that you get just from defining the model space as a diagram. And lastly, once we've defined that model space, we want to select a model from it. And now we actually have a notion of direction that's meaningful that we wouldn't have if we just were brute forcing all possible petronets or not keeping track of this morphism data. But we actually have a notion of direction in space, and we could even compute discrete gradients to get a sense of like what are productive directions to explore our new space of models. So we can, in some way, efficiently look for a good model for whatever our problem is. Maybe we're trying to fit that experimental data. We could be trying to find the right quarantine strategy that would lower the, minimize the height of the curve of the maximum number of infected people. So there's lots of arbitrary types of evaluation criteria you could have at this point. And so that was the second project I wanted to highlight, and I want to finish by talking about agent-based models, which is a type of way of simulating out our disease models. So given a particular petronet, we want to then see how do we actually create that program which evaluates it. So the main mechanism by which we update some state of the world is like a discrete dynamical system is a rewrite rule. And the general formula for rewriting some state of the world is to have a pattern. You match a certain pattern, a little sub-piece of the world. You then delete something in it, possibly, and then you also insert something, possibly. And this notion of rewriting from category theory captures the data of all of that with something called a span of morphisms. But it's really intuitive that the left-hand side is just the pattern that we're trying to match. The middle is this subset of that which is not going to be deleted. And the thing on the right is the thing you're going to update with. So basically, anything that's on the left that's not in the center gets deleted, and anything that's on the right that's not in the center gets added. And I think it's a really important takeaway that this is an inherently dynamic process, yet somehow we've managed to encapsulate that whole dynamic process with this very static object. This is just a piece of data that's sitting. It's not lines of code. It's not a function. But by giving this the right semantics, we can use it to actually make things change. And another key point is that I showed an example for rewriting of graphs, but because this is defined in a categorical way, it ends up being valid for any cset and even things more general than csets. And so that means that the same 20 lines of code end up being useful for any kind of rewriting graphs, rewriting entire neural networks, rewriting pie recipes. So it's a very powerful idea because so little code can actually take you so far. I want to show an example of a rewriting just so you have more intuition for how it works. So this would be a particular graph that we want to apply this rule to. And when we apply it, we essentially match these three nodes here. We do something called a pushout complement, which performs this deletion, and then we perform something called a pushout, which then adds this extra edge in the reverse direction there. So that's an example of basically firing this rule on this graph as the input. I want to also mention that what I showed you was called double pushout semantics. There's a notion of single pushout semantics, which the real difference is that when you delete something, it sort of has this cascade delete effect. So in this example, I have a blue dot here that is deleted, and you know it's deleted because it appears on the left but does not appear in the middle. And now I want to essentially delete the blue node here. Now my pattern makes no reference to this lavender triangle, but because that triangle is implicitly connected to that node that I just deleted, the lavender triangle also gets deleted. So this is an example of that generality where I can take the same rewrite rule and give it different semantics. So there's even other semantics we can give, and we're free, we're at liberty to choose which semantics we want on the fly, essentially. So I want to return back to double pushout rewriting and focusing on rewriting a very specific type of cset, which is what I'll call the SIR cset. The structure of that cset has just 3 dots in it and no arrows. So the meaning of a cset with this schema is to say, I have a certain number of susceptible people, I have a certain number of infected people, and I have a certain number of recovered people. And that's all you're saying with a cset of that schema. So we could perform rewriting on that schema. And you might imagine that from the petronet itself, we can automatically generate these two rewrite rules just from the structure of the petronet. So one of those rewrite rules says, I want to find a match of an infected person and a susceptible person. And I want to replace that with two infected people. And another rewrite rule that you also could have generated automatically is I want to take an infected person and replace it with a recovered person. So moving beyond a toy example, we've made the schema a little more complex in order to basically tag each of these circles with a certain number, which is going to be the person's age. And so this is important for making the model more realistic because different age groups have different interaction patterns, and actually empirically you get much more accurate results if you are able to distinguish these different types of infections. And so we might ask, how do we want to represent this? Do we want n squared different rewrite rules, or do we actually want just one rewrite rule and sort of one line of arbitrary code, I would say, which looks at the things that you match, looks at the numbers, and then computes the right thing? So I'll say this is an honest trade-off that you have to make, because I think that the n squared rewrite rules are completely transparent to a computer, because computers do not interpret arbitrary code without really restricting the type of code that's there. But I would say that this other option is actually much more intuitive and understandable for a human being, writing that code or reading it. So importantly, we're at liberty to make this trade-off. And so working with Sean Wu, we actually took this second option. We used data from a Taiwanese organization that was actually gave us real coefficients for the different interactions between the different age groups. And for example, because the eldest age group is not as in contact with people as working age people, the total fraction of infected people in that age group was lower. And so essentially, we are able to implement this agent-based model framework, not only for the SIR model, but implicitly, that was our goal, but in effect, we created one for every possible cset. So this was like a very powerful tool. And the last point that I want to really stress is this issue of transferability. So I want to give a concrete example of a data migration that's really useful. So what I've been describing is this SIR model, but now imagine that our perspective on reality changes and we realize we need a richer model. So it turns out that susceptible and infected people have doctors, and it's possible for two people who share the same doctor to infect each other by a totally different mechanism. Maybe it's in the waiting room. So in order to represent that, we need a new schema that looks like that, and we need a new rewrite rule, which specifically matches susceptible infected people who share a doctor. So the problem is we might have done a lot of work related to sort of from this frame of mind, and which means all of our data structures and our data is in the form of this schema. So how do we sort of import all of this work into our new schema? So you might imagine that it's at least at the schema level, it's easy to say what the relationship between these two is. The S should map to the S, the I should map to the I, the R should map to the R. It turns out that is sufficient information to specify in order to migrate our old rewrite rules into our new rewrite rules. So there's this notion of a push-forward data migration, which is going to actually do semantically the right thing, which is to give all of these people their own doctor and to not do anything else with that information. And so essentially, because we represented our algorithm as these data structures, we are able to migrate our algorithm into a new perspective. And I think if you're really just used to thinking of algorithm as code, that will be a really mind-blowing idea, because it's really the kind of high-level transformation that could not be done if you were representing this in any kind of script. So I think I gave a really broad list of examples throughout that talk. And I think there was a unifying theme, though, which was that math, code, and formal logic, they're really powerful, they're really great, they can represent anything you want. And it's easy, and I once felt that they're the only possible kinds of syntaxes that can represent things formally. And they're very expressive, but the trade-off there is that because they're so expressive and powerful, it's really hard for human beings, and especially computers, to make any kind of inferences that we would want to make about them. And on the other hand, these combinatorial data structures, they are still formal. They're tailored to a specific domain, unlike logic, which is very general. But it's not such a handicap that they're tailored to a specific domain because, as I showed, we have a language for moving information between different domains. So it's not really such a handicap. And because of their nature, there are very intuitive and diagrammatic syntaxes also that end up being very applicable for them. A theme was that when your model is data rather than code, that's a very different way of thinking about models, and the consequence is that they're much more readable, they're easier for humans and machines to infer things about. And I think also a recurring theme throughout the talk was that when we model a domain with c-sets, they're very general, but also a lot of the algorithms that I talked about are made possible because you are working at that level of abstraction. So it's a good idea to try to think about how do you cast your domain into the language of c-sets or those related structures. So with that, I want to thank the team at Topos and being advised by James, as well as working with Sean and Andrew. And yeah, happy to take any questions.
Yeah, thanks. That was a great talk. I had a question about the model selection part.
Yeah.
Which is always a very challenging problem. So it looks like if you have the kind of model inclusions like you have in these diagrams, then by setting appropriate rate constants to 0, you should always be able to any fit you could do with 1, you could do with the thing it's included in. And so you would assume that if your optimizer is working correctly, you should never do worse in terms of fit by choosing a larger model. But of course, there are other considerations involved in picking models that have to do with all sorts of other things. So I was wondering whether you tended to tackle that aspect of it.
So that is true of specific problems. So the particular loss function here of fit the parameters of a petronet to some data, then that does play nicely with the structure of the homomorphisms, where the actual data of the homomorphism is actually going to tell you how to set the parameters to make it an equivalent petronet. I don't actually think that that's a good, I don't think that once I've solved this petronet that I should use that petronet in order to initialize the.
No, I agree.
Yeah.
I'm just saying that you should always expect to do better by picking a more general model, at least in terms of fit to the data that you have, right?
Yeah, I think that would be an example of a structure that plays nicely. So
right.
if it plays.
Kind of plot I'm thinking of. Yeah. Okay.
Yeah. So we can choose your structure. So we can really, there's a lot of flexibility in taking a bunch of objects and defining a category around them. So you're not fixed for there's a natural choice for petronets, but you could definitely choose other types of morphisms between them if you had a different problem. But yeah, in general, to make this loss landscape predictable, and you would want something that's concave really, so that or convex, sorry, so that once you start, you're exploring, and once you start seeing worse models, oh, I can stop going that direction. If the loss landscape was completely unpredictable, you wouldn't know when to stop exploring, really. So.
And do you have methods to try to tackle that, or is that something?
So that's a feature of your choice of the problem and the structure. So we haven't yet made some automation of picking a structure that matches your problem exactly, but we can at least classify if if this property holds of the diagram in your loss function, then you can expect a curve like this and exploit that in the exploration process. But if our loss function was the try to lower the curve metric, then maybe this wouldn't look so smooth, and that would be like a trade-off that you make. But these are independent variables. So, but yeah, this is yeah. So my hidden slides. Or I'm not sure what's the right one. Maybe this one is like the summary slide of all the things that are going on.
I was wondering if you could maybe go back to the single pushout slide.
Yeah.
I have a question about that.
Sure.
Yeah, so I was wondering if you could explain this diagram for a second.
Yeah.
So these, well, what are these?
Yeah. Well, there was a little thing I omitted, which is that you could sort of ignore this center thing. So like this kind of diagram is not representing the middle structure in this span, but so that could be one point of confusion that I should have said.
So are these dashed arrows spans?
Yeah. So these are there's a difference between double pushout in the category of, let's say, graphs versus single pushout in the category of graphs and partial morphisms. So these dashes are supposed to mean like it's a partial morphism, which is really just the data of a span like this where this arrow is monic. So that allows you to add and delete, but it just happens to work out that when you delete this way, it has this cascading effect. Whereas in DPO, so I could delete this vertex without deleting those edges. I could try to, but there's a rule which says that's an invalid DPO rewrite rule, and so you're just like forbidden. There's a way of checking whether or not you're doing a rewrite rule that would leave dangling edges, which is bad, and would create something that's like not a graph. So essentially, DPO has you on guardrails and says you can't delete things if you're not going to explicitly tell me you're deleting them. Whereas single pushout is more Wild West and says, okay, try to delete that, but I'm going to delete everything else I need to make it a valid instance.
Yeah, thank you.
Cool.
Maybe this is a good time to stop
Sure.
the recording then.
Okay.
Why don't we thank Kris again?
Thanks.